Yeah, thanks very much for coming. My name is Bryan Boreham. I'm an engineer at Weaveworks, and that's my Twitter handle, which is the main reason I'm here. No, I'm here to talk about Cortex, and I gave this the clickbait title of Infinitely Scalable. So who came because they were kind of riled up, like, there is no way it can be infinitely scalable. So, welcome. And then when I was thinking about the name and kind of running it around in my head, and somehow it turned into Infinity War, you know, which was a film that was out recently, and it's kind of a dumb film. They go chasing around after these stones, infinity stones. So I'm not going to mention any of that again. So Cortex is a time series store built on Prometheus. Who uses Prometheus? And I put my own hand up because we also do use Prometheus. It is built on Prometheus. We have huge reuse of the code, very much built on it. Great benefit of the open source community. And the key attributes of Cortex are that it is horizontally scalable, highly available, provides long-term storage, and is a multi-tenant system. So I'm going to say a lot more about all of those things over the course of this talk. Cortex is a CNCF project. We started at Weaveworks. We turned over the IP to the CNCF. It's Apache licensed. You can fetch the source code from that URL at the bottom of the page, project/Cortex. Okay, why did we build Cortex? Well, Weaveworks, we run this software as a service, monitoring, observability, and continuous deployment platform, Weave Cloud. And we wanted to do things like dashboards. We draw these automatic magic dashboards. And we wanted to do that as a sign up. You know, you can just show up with your credit card and sign up. We didn't want to have to provision Prometheus to every individual user, so we wanted a multi-tenant system. So that's the genesis of the thing. This is the minds behind Cortex. This is a screen dump from GitHub. So it started June 2016, 2.5 years-ish. We've been running it in production about 2 years, probably. The #1 committer, Tom Wilkie, in the audience. We got a few of the maintainers of Cortex here. We got Ken here, myself, and there are people on this list who are also maintainers of Prometheus. So again, I want to stress a lot of sharing and collaboration there. You probably can't see on the screen, but I do find it amusing that the number of lines deleted is higher than the number of lines added. So I guess he's #1 in a way. Anyway, so yeah, the community, the minds behind Cortex. The other side of the community who uses Cortex, it has been adopted by a number of people running platforms. Weaveworks, obviously, Grafana Labs, Aspen Mesh, and Platform 9 are here at KubeCon, and as are Maya Data, OpenEBS, they're part of. The people on the right are some of the users of some of the platforms on the left. And I put this, so this is the soul of the project. Is anyone liking the dumb infinity stone metaphor? Yes, okay, 1, good. I pleased 1, thank you. Anyway, Yeah, so let's take a look. I mean, most of you put your hand up that you use Prometheus, so you probably have a pretty good idea how it works. But just to cover the basics, Prometheus runs as one process. That's one of the key things, very simple. Just run it, and you point it at things that have metrics, which might be your own apps, or it might be some kind of exporter that gets data from somewhere else. We call this scraping. It pulls the metrics in, it compresses them, stores them on disk, and it also serves up queries, which come from some kind of dashboard viewer, something like that. So that's the basic operation of Prometheus. So problem comes when you have more things, more apps, more nodes, more everything. What are you going to do? Well, you can just get a bigger box. Prometheus scales really well. You can certainly serve millions of time series from one large Prometheus box. Very effective, very good, very well engineered. But some people then find that tops out. Still not, can't get a box big enough, or don't maybe want that much risk in one place. So the next place that people go is to split up the problem. So at this point, you have to kind of pick. You're manually sharding the data. Whether you slice it by apps versus infrastructure, or you slice it by team A versus team B, or you slice it by data center, or however you slice it, you are going to have to pick. And then that leads to a problem in terms of viewing the data. How do you build one chart that brings together data? How do you get a global view of the data that you've split up? So that becomes a problem. And there are ways to solve it in Prometheus, but it gets pretty complicated. So we wanted to do that differently in Cortex. Instead of one process, we run many processes. It's what Tom calls a microservices-oriented architecture. Flame me about that one. So this is the Cortex architecture. We actually use standard Prometheus to do the scraping, the operation of pulling in the individual metrics from the endpoints. They are sent to a distributor process. They're compressed, they're stored, and we have a query process. And it's split up into multiple pieces. So let's walk through each of those in turn and talk a bit more detail about how they work. So the thing that processes time series samples coming in on ingest, we call an ingester. So yeah, the point of my infinitely scalable headline is it's horizontally scalable. If you need more power, you add more ingesters. We route through a process called the distributor. We route every time series to one ingester. We do that using a technique called a distributed hash table, DHT. You can Google that. I've got a link there if you want to read one of the seminal papers about that idea. Actually, I want to stress Cortex is built on like decades of work and research that other people did. Very, very well-worn techniques for distributed databases, basically. So I don't want to claim any of the insight or ingenuity in taking those ideas. These are pretty standard ideas, but they're also pretty good ideas. So the great thing about a DHT is there's no bottleneck in terms of coordinating. You can keep on adding ingesters, and they will be inserted into the DHT, and we'll route time series to one ingester. And they don't have to, communicate every single time to one central point, which is going to limit scalability. So a distributor working through a DHT gives us, for this piece, gives us infinite scalability. Let's look inside one of those ingesters. So the samples come in. Each wiggly line here is time series. Actually, in reality, most time series are 0 continuously. It's kind of dull when you look at it. But I've imagined that all of my time series are much more exciting here. So the wiggly lines come in, they build up at different rates, and they're compressed in memory. The compression technique that Cortex uses, and basically every time series database I know about uses, is called Gorilla compression, came from Facebook. Link to the paper there. So we compress it, we get this massive compression of the data, and when we reach a certain level, which is, well, originally it was 1K. Recently we've brought that up to sort of 4 or 5K. Typically a few hours of data in one chunk. We stick the chunks in a store. So this is the power of the infinity stone. The space stone is compressing our data. We do store it in memory for a few hours, compressing it, and then we send it to the store. Oh yeah, I wanted to mention the store has the basic data. It also has an index. I'll talk about the index in a minute. So we're going to store the data for a long time. What do we want from that? We want scalability because we're infinitely scalable. That's why you came. We want speed because we don't want to wait any time at all for our dashboards to draw. The third thing you might not be so immediately aware of, durability. What do I mean by this? So you can put something on a disk, and if you're going to store it for years or months or whatever, if you're going to store a lot of it, we have hundreds of terabytes of this stuff, then your disk is going to fail. So you need to store multiple copies on disk to save yourself when one of those copies fails. And then when one of them inevitably does fail, you need to make a new copy from one of the other copies that you were hanging on to, right? That's a kind of anti-entropy function, they call it, in order to have durability for the long term at enormous scale. So that's a lot of work. And if there's one thing I can tell you about me and Tom, we don't like doing any work. So we get someone else to do that work. So Cortex can speak to a variety of back-end stores. Cassandra, very well-known one, DynamoDB or S3 from Amazon, Bigtable, Google Cloud Store. So there's two kinds of store on there. The table-oriented ones, like DynamoDB, are used for the index, and the sort of bucket-oriented ones are generally used for the chunks, the actual time series chunks that we've stored from the ingester. Although that isn't an iron rule, we do also have the capability to store chunks in DynamoDB and in Bigtable and in Cassandra. So anyway, there's actually more backends coming. It's quite a nice kind of adapter pattern. Yeah, we do rely on someone else to do this work of making the data durable, and also running index lookups at enormous speed at enormous scale. So look a little bit more into the detail of the index. It's called an inverted index. What do we mean by this? So I've got an example there of a Prometheus metric. So every metric has a name, HTTP duration seconds in this case, and it has a set of labels, and each label has a value. So job equals shipping, instance equals A, path equals foo, result equals 200. The average tends to be about 10, 12 labels per metric. And the concept of an inverted index is we break all of those values out of that row, and we store them separately. We store a list against those. So, so we kind of have an index for each label against each metric, and we have all the possible values pulled out there. And then against those, we have all the time series. This is basically the way Google indexes the web, right? For a word that you're searching for, Cortex, they have a list of all the web pages that mention that word. Let's look at the read side of that. If we have a query, a PromQL query, I want to summarize or view all the time series that have job equals shipping. What I do is I go to that row in the index, first of all, for the job label. Look up shipping, that gets me a set of time series. For each time series, I look it up for the right time boundary, the last hour or the last week or whatever. That gets me a set of those chunks. I bring the chunks in and unpack those into the individual samples. So that's the inverted index. Again, not a novel technique. I'm just kind of going through how it works, but pretty common technique for this kind of large-scale database. Okay, so back to my picture at the beginning. This is the querier piece. And again, this is horizontally scalable. I can add queriers. If I have more people looking up, more people viewing dashboards, I can add queriers. They're all independent. They just talk to the store. The store is massively scalable because I'm paying Amazon vast amounts of money for it, or whoever, Google. Other cloud stores are available. One little wrinkle, I mentioned that the samples are compressed in memory. They're kind of chunked up to a few hours in memory. So we also need to go to the ingesters to get that last couple of hours of data is going to be in memory. We need to check there as well as in the store. And then we do like everything to go fast. So we put a cache on there. We do a lot of caching. We cache index lookups, we cache chunk lookups, we cache partial results, we cache a lot of things. And to stress the microservice nature of this, the fact that we've broken it up into pieces, lets us, maybe this is a place where we kind of innovate a bit. We get creative and add more kinds of queriers and more kinds of caches, and we can do that fairly freely because it's all split into bits. Okay, so put it all together. Oh no, one more thing. Sorry. Yeah, reality. So maybe some of you are thinking, hang on, you're holding my data in memory for hours? What happens if it crashes? Obviously, my software doesn't crash, but you might have patched it or something, or it might crash. Anyway, the answer is we actually send each sample to 3 ingesters, and we hope that all 3 of them don't crash. That wasn't a joke. Right. Yeah, so so the DHT is actually used to pick a consistent set of 3 ingesters for each time series. We build up the samples in memory 3 times over, and we send them to the store, and we deduplicate later on query. Okay, so now we can put it all together, right? Yes. Spent minutes on these slides. Yeah, put it all together. This is our infinitely scalable Prometheus. Each Each section here, we can just add processes. They do not interlock. They do not intercommunicate across the vertical segments here. Many Prometheuses can be sending data in. They go into many distributors. They probably go through some kind of load balancer, like an ELB or something like that. Distributors use the DHT to pick ingesters. Many ingesters. The ingesters write to a NoSQL store, which is massively scalable, has however many hundreds of disks. We can have as many querier processes as we like, and we serve it all out to as many users as are visiting our site. The whole thing is multi-tenant, front to back. So we give each, we call it an instance. Think in terms of you as a user of the system might have your dev instance, your staging instance, your production instance, or however you want to think of these things separately. So an instance is not necessarily one customer. Could have multiple instances, but each one has a key, has an ID. That ID is carried through the system. The ID forms part of the index, so we can look up queries for one instance at a time. And the whatever is on the query side, that we build dashboards. You can use something like Grafana because Cortex speaks the exact Prometheus API that Prometheus does. So anything that will talk to Prometheus can be used on the query side. Anything that can provide metrics to Prometheus can be used on the scraping side. And we maintain that multi-tenant ID all the way through. So that is the big picture of our infinitely scalable Prometheus. Now, I wanted to mention, there's one character who I haven't mentioned yet in the film. Well, a little bit later, Thanos is the name of another project, which is also on GitHub and also seeks to provide highly available Prometheus and long-term storage. It's quite a bit newer than Cortex, about a year or so old right now, and they set out with a rather different aim, which was to try and keep things simpler, trying to keep things closer to the native Prometheus. What is interesting is it's kind of edging. I mean, you can tell from the picture here, it's edging up in complexity. They certainly have more components than they started with. But I think what is good is to look at the similarities. Both projects have a huge reuse of Prometheus code. Both have this aim of when you've split up your metrics to begin with, because they're in different data centers or something like that, and you want to bring them together into a global view. They both have that feature. They both have this split between recent data. In the Thanos case, the recent data is just in the Prometheus, and Prometheus writes it to disk. They take those disk blocks and ship them off to long-term storage, like an S3, same kind of thing. But there is this split, same in Cortex and in Thanos. There's cloud buckets like S3, and as I said, they do have multiple components in their architecture. So yeah, a lot of similarities between the two projects. I'll just point out the big difference is multi-tenant, right? Cortex is a multi-tenant system. We needed that. We were building a cloud Prometheus as a service, and we didn't want to kind of install a new Prometheus every time a customer turned up. So Cortex is multi-tenant front to back. Cortex does this automatic sharding based on the distributed hash table. Thanos is kind of starting from the standpoint you've manually divided up you have these Prometheus running separately to begin with. Yeah, differences in the storage format. So Cortex does what I call query sharding. So if you do a 30-day query, we'll actually run 31-day queries in parallel to speed that up. That's a feature Thanos doesn't have. Thanos does downsampling, so they can take your older data. Maybe you've sampled it at a 5-second interval, and they can downsample it to a 1-minute interval. We don't have that feature. So healthy competition, different projects, different aims. And I got to make a joke about a film. So I said on the description of the talk that I talk about our experiences in production. We have been running it nearly 2 years. So one of the things is that anyone can sign up. You know, if you show up, you get a free trial. So anyone can kind of, I imagine some of you are in this room pointing your notebooks at my service and trying to break it. Yeah, this should be fun. Well, anyway, on any random day, someone can show up with data that we've never seen before or data in quantities that we've never seen before, and we need to deal with that. So we learned a lot about scaling a big back-end system. One aspect of that, these NoSQL, the index basically, is hard. Getting that to scale, getting it to run efficiently. There's these two things that are kind of pulling in opposite directions. You want to parallelize what you're doing because you have a big back end. This is where I'm talking about something like Bigtable or DynamoDB. Amazon and Google and so on, they run that at a huge scale. So on our side, on the code, we want to talk to it as many times in parallel as possible. However, on the flip side, you need to batch up your requests, otherwise the per call overhead is very high. And those things are pulling in opposite directions. So kind of tuning and tweaking that is a lot of the work that's gone into Cortex. Also tuning the schema, hotspots. If you write to the same place in terms of the underlying data store, if you write to the same place too often at the same time, it'll choke. We're actually on version 9 of the schema of exactly how we do that. And hilariously, we have to maintain all the code for all the previous 8 schemas is all still in there because we actually used this thing in production. We still reading some of that data. Other experiences out of memory errors. I don't know. Yeah, that's. I guess I'm just looking for sympathy here. High cardinality queries. It's been a little bit of a theme in some of the observability talks around here. High cardinality, basically the meaning a lot of time series behind one metric. And by a lot, I mean 10 million. So it says in the Prometheus documentation that 100,000 should be no problem. And that's true enough. How do you get to those numbers? Basically by putting something like your client IP in as a label. If you have 1 million customers, well, actually, even if you only have 1,000 customers, but you're running your service on 1,000 machines, then it multiplies up. So you have 1 million time series now. So there's that kind of effect. The labels multiply, and we basically, that's still a challenge. At some point, we bring all the data into memory in order to summarize it, and the thing will blow up if you've got too much of it. What else? Short-lived time series, yeah, that's another thing. The metadata basically dwarfs the actual real data. Anyway, looking forward, we are trying to have a write-ahead log, meaning we stick stuff on disk early so that if we have a crash and we lose everything in memory, then we don't lose hours of data. So that's the flip side of when I said earlier, we just hope that all three of them don't crash at once. If we have a write-ahead log, then that's less of a danger. It is a very complicated beast, Cortex, because of all these multi-processes, microservices, pretty complex to run. So Tom's been working on a simpler config for that. Oh yeah, we run rules like alerts and things. That is not currently sharded. That needs to be sharded for scalability. We might add downsampling. But anyway, I hope we get more users. I'd love any of you to join up as a user, an adopter, as a contributor, if you like. It's an open source project and it grows with the community. Yeah, please visit the project. Take out your phone or your laptop now and star on GitHub because my pay is directly tied to the number of stars. No, it isn't. Yeah, thank you. I guess we have time for a couple of questions if anyone wants to go there. I have a question back there. I have a microphone. Do you want to try shouting or?
Yeah, sure. So on the ingestion path side, if I have a HA or mirrored Prometheus pair, I believe Thanos does dedupe. Do you guys handle that as well?
Yeah. I guess the point you're making is that on the scraping side, there's a single point of failure. Yeah, in the Thanos project, the way you deal with that is by running two of them, scrape everything twice, and then dedupe. And we do not have that feature in Cortex. I mean, basically, we're not putting any. We're not getting that process to do any work. Okay. In the Cortex model, it's just scraping and immediately sending the samples. So if something goes wrong with it, if it crashes, it'll just restart. It's really in the Thanos model, it's holding a lot of data and it's used for queries. So it's more important that it's HA. In the Cortex model, the originating Prometheus is kind of ephemeral. If it's sending us samples, we've got them. If it's got a problem, it's not sending us samples. So yeah, that is a feature we could add, but it's less of a sort of critical point in Cortex.
One more quick question. The alert rules and recording rules. So I understand at a high level, I can look at your system as a long-term retention and global query. Can I also define alert rules and recording rules at a global level on the ingester nodes or somewhere?
Yeah, so we have a component called the ruler, which runs recording rules and alerts, just exactly the same way as Prometheus runs them. And I didn't include it in the talk for reasons of time, but yes, it exists.
Hello?
Hi.
Hi. So you were talking about the flush failures in the ingesters.
Okay.
So what is the common approaches you take to solve those type of problems? Is it like what I'm thinking is it's like the ingestion is happening very fast versus the system, the storage is not able to handle the load, right?
Yeah, so your question is, I talked about ingesters getting choked up and being unable to flush.
Yeah.
What causes that? So in DynamoDB, well, up until about 2 weeks ago, you had to pick a capacity level. You paid pre-selected the capacity level. So if you select that too low, then it'll just back up in memory. And I'm sure I am one of the top 100 experts in the world on scaling DynamoDB because I've done it 1,000 times. I'm also one of the top 100 people in the world for modesty, yes. That's one reason, yeah. So if you, for whatever reason, if you're running Cassandra yourself, you'd have the same problem. You've picked a fixed level of capacity And if you're trying to flush chunks faster than that. So what is nice is the ingesters can kind of grow and shrink. They don't need to flush immediately. You can have a 1 hour backlog, as long as it's not going up forever. Yeah. As long as it comes down at some point, you find some more capacity, find a new credit card to put on the Amazon bill. So that's one reason, just not enough capacity in the back end. Some of that stuff like short-lived time series is a surprising problem. Like I mentioned on the slide, Apache Spark will like run pods for 10 seconds, run like 1,000 pods for 10 seconds. And so we barely get one sample. Actually, what we should probably do is throw it away because very little you can do with a query. But that has been a case. You know how I said any random person can sign up on the web? We have limits in there now. We have a bunch of kind of soft limits in the software to kind of avoid just getting taken down by someone who has an exciting kind of data. But that's another kind of reason. If it's just a lot of tiny chunks, then it's going to need a lot more resource than you were thinking of. We're at time. Okay, well, thank you very much. I'm here all week. Come to the Weaveworks booth.